All right, so in this video, we're going to basically kind of talk about how to predict the number of covalent bonds an atom will form based on its position on the periodic table. All right, so we could use the periodic table to kind of predict this. And for most cases, we'll be right. There are some exceptions, and we'll talk about those exceptions a little bit later. But what I want to kind of highlight to you guys, what you see here, is that based on the periodic table, you could kind of quickly figure out how many valence electrons a particular atom has, right? And now we're going to really focus on the nonmetals because we're talking about covalent compounds. But up here you see that how many valence electrons these particular atoms have, right? And so hydrogen has 1 valence electron, the carbon group has 4, the oxygen group has 6, the halogens have 7, your noble gases for helium has 8 valence electrons. Okay, and so now knowing the amount of valence electrons, we can actually kind of predict how many bonds do these atoms need in order to have a full valence shell. All right, and the way I kind of look at this, and this kind of works for most atoms, most nonmetals. As I said, there are some few exceptions here. But if you notice, the number of valence electrons and the number of bonds needed, most of the cases will add up to 8. All right, and so let me show you what I mean by that. Like if you look at carbon, the carbon group has 4 valence electrons. All right, so that means in order to reach its octet, the carbon needs to make 4 bonds. 4 plus 4 equals 8. Okay, let's look at this one, nitrogen. Right, nitrogen has 5 valence electrons. Okay, it needs 8 to fulfill its octet, so that means it needs to create 3 bonds. Okay. Oxygen has 6 valence electrons. Okay, to reach the full octet of 8, it needs to have 2 bonds. Same thing with sulfur here. It also has 6 valence electrons, so it needs to make 2 bonds. 6 plus 2 is 8. All right. Fluorine, chlorine, bromine, iodine. These guys, they all have 7 valence electrons, so they only need to have 1 bond in order to have 8 or have an axis of 8 electrons. And then we have this group, the noble gases. It's really difficult for them to bond with anything. All right. Usually, well, the elements a little bit lower they can, but like helium, neon, and argon, they don't react with anything. But that's simply because they have a full shell. Right, and so because they have a full shell, it's very difficult to get these atoms to react to anything. So let's put into what we just talked about to application, right? All right, so let's consider this compound here. So I have this compound here. All right, so now let's look at this compound. It's CBr3. And the question I have is this compound or this molecule likely to exist? Based off what we were just talking about, can this molecule exist? All right. Pause the video, kind of think about it real quick. All right, so let's look at our periodic table and let's discover this, right? And so what we see here, we said that bromine, because bromine has 7 valence electrons, right? It only needs 1 bond and for it to have its full octet. All right, and when we're looking at what we have here, we see that that's the case. Here's our bromine and it's 1 bond. Bromine is 1 bond. Bromine and it's 1 bond. Okay, so it has access to 8 electrons. Now let's just make a couple of things clear so that we understand this picture here. Every time when we draw a line, all right, every time we draw the line, this line basically represents 2 shared electrons. Okay, and so now when we're looking at this, if we were talking about bromine here, all right, then we could count up how many electrons this bromine has access to. All right, and it has access to 1, 2, 3, 4, 5, 6. So these electrons in the outside, we call these lone pair electrons. Okay, so we see that we have 6 lone pairs, or 3 lone pairs, the 3 lone pair sets of electrons. So we have 6 electrons, all right? And then we got to count this line here, and this line represents 2 electrons. So 2, 4, 6, 8. So this bromine has access to 8 electrons. And we could look at all the other bromines and we could see that it's the same thing. So you have 2, 4, 6, and then here's your 8th electron, okay? 8th set of electrons. And here, 2, 4, 6, 8. We got 8 electrons there. So we're good with the bromine part, right? Because we see that halogens only need one bond in order for it to have a full set of electrons. But now if we look at carbon, all right, we say that carbon needs 4 bonds for it to have 4 sets, for it to have 8 electrons. Now if you're paying attention, you see that we have 1 bond, 2 bond, and 3. So the carbon doesn't have its 4 bonds. So really, when we think about this compound, all right, cannot exist as written. Okay, let's look at another example. So let's say we have ICl. Can this compound exist? Well, if we notice, we have both I and Cl, they're both halogens, and they both, if you see here, only need 1 bond. Okay, so let's look at this. Did iodine make 1 bond? Yes, here's its one right here. Did chlorine make its 1 bond? Yes, it's right here again. So we see here that they both have 1 bond. Now, if you could also count up the electrons, and that way you could kind of double check yourself. Well, you have like 1, 2, 3, 4, 5, 6 that comes from the lone pair, and then you got the shared set of electrons between iodine and chlorine. So yes, we have 8 valence electrons here. Let's look at chlorine. We got this 2 that's being shared between the iodine and chlorine, and then you got the lone pairs, the 3 lone pairs. So 2, 4, 6, 8. So this chlorine has also 8 valence electrons. So we see that this is a good picture. All right, this one's correct. Let's look at another example. So let's say if you have a compound that looks like this. Is this a viable molecule? Can this work? Well, let's look at hydrogen, right? We mentioned from this periodic table here that hydrogen only has 1 valence electron and it only needs 1 bond. By doing so, it will look like helium, right? So let's look at this example that we have here. Well, here's hydrogen and it's 1 bond. All right, so we're good there. Hydrogen's good. All right, but what about fluorine? What about this guy? All right, he's a halogen. All right, we see that in your halogens, there's 7 valence electron and it only needs 1 bond. And if you're looking at this and if you're paying attention, how many bonds did we have here? Well, we gave fluorine 4 bonds. So we could conclude that this is incorrect, that this cannot happen. Okay. All right, let's look at one more example. So let's say we have this compound here. Whoops, wrong letter. Okay, we have this compound here. Can this work? Okay, hydrogen, once again, only needs 1 bond. All right, so we're looking at the 1 bond of hydrogen. Cool, perfect. But what about sulfur? Well, if you look at the periodic table, sulfur is in the oxygen group. And if you see this, they have 6 valence electrons. And so because they have 6 valence electrons, 6 plus what equals 8, that means it needs 2 bonds. And so when we're looking at this, the sulfur has its 2 bonds. Yes, it does. It has 1 bond here, another bond here. So that means this overall compound it's viable. It's good. All right. So this is the way that H2S will exist in nature. Now, with all rules, there's always exceptions. All right, and so let's kind of address some of these exceptions. One is boron. Okay, boron is just an element that really it only needs to have access to. It only needs to make 3 bonds, and it's fulfilled this octet. So you will have compounds like BH3 And this is a real compound. Okay, it only needs access to 3 bonds. So only needs to have access to 6 electrons, or it has 3 bonds. And so that's the way that boron typically works. And then you also have another set of exceptions where you have elements that can actually have more than 8 electrons, and we have access to more than 8 electrons. So for example, like phosphorus is an example of this. It could have legit attached to it 5 chlorines. All right, this is called phosphorus pentachloride. Okay, now here we see that phosphorus has 10 valence electrons. Whoa, how does it have 10 valence electrons? Well, what we find here is that basically starting from the 3rd period and down, all right, so 3rd period, 4th period, 5th period, 6th period, all right, these elements now have access to the d orbitals, because if you recall, the d orbitals actually start showing up in the 3rd period. So because now it has access to the d orbitals, and is within range, it actually could make, and only if it has to, it could actually make more bonds past the octet. All right, so we typically call this the extended octet rule, or it's extended octet exceptions, because elements from the 3rd row down, are the nonmetals from the 3rd row down, could actually achieve this, where they have more than 8 electrons in its valence shell, and that's because they have access to the d orbital. So electrons could actually then start filling up the 3d, without necessarily having to move up to the 4s and so off and stuff like that. So that's the reason. Okay, if you really want to know the reason why.